This video is on the objective determine the critical value or critical values, if it's a two-tailed test, for a hypothesis test for the mean of the differences for the paired data in order to define rejection regions, right? Once you've found those critical values, right, you can establish a rejection region or regions. All right, and we've seen the paired data before. Anytime you see the words paired data, that means you're looking at two dependent samples, right? Every pair of data is related to the same object or the same person. Thus the relationship, the dependence between the samples. So let's take a look. All right, so as with every video, it's like, hey, if you're unfamiliar with the topic, want to see more about it, click on More Instruction. Look at their videos, their notes, their examples, and hopefully those all help you out. Okay, so here, a researcher wants to test to see if husbands are significantly older than their wives. To do this, he collects the ages of husbands and pairs them, right, paired data, pairs them with the ages of their respective wives for a random set of married couples, right? So this is paired data because you have the husband age, the wife age, and that pair of data is related to a single couple, the same couple. So that's why these are, dependent. You can't switch the data around. Suppose that the data were collected from a random sample of 12 couples, where each difference is calculated by subtracting the age of the wife from the age of the husband. Assume that the ages are normally distributed, right? That way, because this is a pretty small sample size, if we assume that the ages are normally distributed, then the sample size won't matter. 12 couples is fine, and we'll be working with that student's t-distribution with 11 degrees of freedom, right? Because we're going to be looking at 12 differences, right? One sample of 12 differences. And a t-test for one sample with a sample size of 12, the t-distribution has 11 degrees of freedom. It's the sample size minus 1, the number of pairs minus 1 in this case. So the first question, before we even get into the critical value, is what type of hypothesis test is this? Is it a right-tailed test, a left-tailed test, or a two-tailed test? So I need to establish some hypotheses here. All right. So remember, for these paired data experiments, you're going to have couple 1, couple 2, and they said that there were 12 of these, right? Couple 12. And there were two samples, but they were dependent on the couple, right? It's paired data. The first sample is the husband height. Right, the heights of the husbands. So let's say I'll just call that maybe H1, H2, down to H12, right, for the heights of the husbands, H for husband, right? And then sample 2 is the 12 heights of the corresponding wives, right? This is wife height. So I'll call this W1, and W2, and W12. Right. Now again, I can't switch numbers in these lists because these are paired. These two need to be next to each other because they're from the same couple. These two need to be next to each other, and so on. And if you recall from earlier objectives, right, if you've been watching, I'm hoping you have. When we have this paired data, these dependent samples like this, we're going to transform it and take a look at the differences. We're going to transform it basically into one sample of differences. All right, now the differences, we'll call them D for difference. They said they're taking the age of the wife, subtracting it from the age of the husband, so it's husband minus wife age, right? Oh, these are ages, not heights. Sorry. husband ages, wife ages, right? Not heights. Anyway, so take the husband age minus the wife age. So then you have, the first difference, the second difference, and then the 12th difference. And then we're going to be focusing on this sample of differences here. Right? This sample of differences has a sample mean, right? And the mean would be called d bar, right? The average difference. It has a sample standard deviation, which is going to be called S sub d, the standard deviation of these differences. And since we're assuming that the ages are normally distributed, if you were to do this for every couple, if you were to do this for every possible couple, not just these 12, and look at, I'm sorry. If you were to do this for every possible group of 12 couples, not just these 12, but every possible group of 12 couples, look at their difference in ages and then the average of those differences. The average of those differences would have a student's t distribution with 11 degrees of freedom, right? The sample size minus 1. Right. And the mean of these d bars would be the mean of the population of differences. The standard deviation of these d bars would be the standard deviation of the sample SD, because I don't know sigma. That's why, if we don't know sigma, that's why we're using student's t, divided by the square root of the sample size, divided by the square root of 12 here. But anyway, that's neither here nor there. What we're asked about here is to set up the hypotheses right now. Right. So what was this claim? Now, it's about mu d. Right? Now, mu d in this case will be the average difference between husband and wife heights for all couples. This is for the population. This is the average difference, or the mean difference, between heights, the average difference of heights between husbands and wives for all couples. All right. And the claim here, what this person is trying to test, says the researcher wants to test to see if husbands are significantly older. Damn it, didn't mean to swear. I said heights again, didn't I? I meant ages. I keep saying heights. It's ages. So this mu sub d is the average difference of the the ages between husbands and wives for all couples, right? The population average difference, or the population mean difference. All right. So this researcher wants to see if husbands are significantly older than their wives. Now, if they did if they're saying the differences were taken as husband minus wife, if the husbands are older, that means that this would be a positive value. Right? If the husband's age is bigger than the wife's age, and the husbands are older, right? The husband's age is bigger, this is going to be a positive difference. So what he's trying to test is this statement here. Is on average for all couples, is the husband's age greater than the wife's age on average, right? So this is basically saying husbands are older than wives on average. Older, right, than wives on average. Okay. Now, that's what's being tested. And once you have what's being tested, the claim or belief stated, then you can set up the hypotheses. Now, this does not involve equality, so this can be represented by the alternative hypothesis. Mu d is greater than 0. The null hypothesis would be the opposite of that, right? That mu d is less than or equal to 0. But again, as you've seen in most of these Newton-Alta problems, Newton-Alta homeworks, they're just going to be writing what they're assuming for the test. So you're going to just be assuming the equal part. So we're going to assume that mu d equals 0. Now this statement, mu d equals 0, this would be that husbands and wives are the same age on average. They have no difference in age, right? Their average difference is 0. So this would be the statement that husbands and wives have, the same age on average. And that's what we're going to be assuming. You're going to assume this, then take through the samples and all that, and finding your test statistic, critical values, rejection regions, all that. You're going to then decide, do you like this or not? Am I going to reject this or fail to reject it? And then from there, make a conclusion about this claim, that the statement that's being tested. All right, now we're asked though, what kind of a test is it? And that's going to be determined from the alternative hypothesis. See, I have my parameter here. This population mean is greater than a value, greater than 0. Remember, when that's the case, this is a right-tailed test. And that's all we're asked for the first part of this. Now there's going to be another part where we have to find critical values, I'm sure. But yeah, it's a right-tailed test at this first option here, because the alternative hypothesis would be that mu d is greater than 0. All right, and then I'm sure there's a second part to this where we have to find a critical value, absolutely. Now notice they're giving us a table down here for t distributions, critical values of t distributions. Now, as mentioned back here, for this particular example, because there were these 12 couples, we're looking at a sample of 12 differences in ages. The distribution of my sample difference means, the distribution of my d bars is going to be a student's t distribution with 11 degrees of freedom. Okay. And let's take a look at that. I'll draw that. All right. Now it's going to look like every other t distribution I've drawn, right? But a t distribution with 11 degrees of freedom. So remember, your number line here represents possible t scores. Distributions is bell-shaped symmetrical curve thing. Underneath the peak is a t score of 0. And it's a right-tailed test, so the rejection region is on the right tail. All right, and I'm gonna try to find this value here, so that the area to the right, this rejection region, this right tail rejection region, I'm gonna find this value, this t-score, so that the area to the right is alpha. And they told us alpha was 5%, right? The value of alpha, the value of the significance level. So I'm basically looking for a t with a subscript of 0.05, right? What's the t-score with 5% above it? And that can be found from our table, right? And you can use a calculator as well, but I'll just use this table they're providing. Again, we're degrees of freedom, 11, right? So I'm in this row here. And then what's the area above that I wish for, right? I want 5% above. So 11 degrees of freedom, 5% above that. What t-score is at? 1.796. So this score here is 1.796. And then if our test, so when we calculate our test statistic, if it comes in above this, we'd reject the null hypothesis. If it comes in below this, we don't reject the null hypothesis. Simple as that. So back here, just what's the critical value I'm finding from this table? 1.796. And show you the same stuff I looked at when I read the table, right? Okay, so again, hopefully watching me do this, looking at the more instruction if you need to, reading the answer explanations when they come up, I'm hoping all this stuff helps you out, when you're going through this on your own. And thank you very much for watching.